I would like to start. If everybody's ready, I want to welcome you to Quantum Computing in Practice. And my name is Etienne. And today I want to make it really simple for you. So I promise it's a really dry topic, but of course, you need to understand it at the end. That's important. So I really promise, and everybody will get the topic. And we have in total 3 episodes. So this one is the first in July, the second, and the third in December before Christmas. And today is more the basics that you can understand what is quantum computing and how does it work. So first, the table of contents. I want to share my intention in 2 minutes, why I chose this topic, and what is quantum computing and how does it work. After this, what is a bit? What is a qubit? Because often you say, yeah, a bit is a bit, but you don't know really what it is, or a qubit. So we talk about it, but we need to look in detail what is it. And the basic of quantum mechanics. What is quantum? What is mechanics? What does it mean? And what are the game changers in the daily life? Examples like a quick walkthrough, where has it been applied already, and what we can do in future with that. So then we will compare the classical computer versus the quantum computers, and also my brain. I made an experiment on the quantum computer. I will share with you, and also I made it myself with my brain, because I can surprise you. You all have a quantum computer in your head. And this is the experiment I told you. We're going to program it on IBM, but just roughly because it's a bit complicated, and I want to give you the basics today. And at the end, we're going or take a look what we learned today with a little conclusion. And of course, I hope there are no questions, but I doubt this because, I promise you today you have all question marks about quantum computing, but I resolve them. I can just make them a bit smaller so that they're just tiny little question marks at the end. Okay, in total, I planned like 50 minutes, and theory and practice is something different. So I think it will be a bit longer than normal, but of course, feel free to leave if you have some calls, or you can continue listen afterwards. So my intention is, of course, I picked the easiest topic on earth. So I wanted to challenge myself, and also I want to bring it closer to you because it was always in the news. And also Pavel from Mimacom, he made 3 years ago, he made a presentation. And this is quite interesting because I didn't listen, but some of you might. And yeah, so you can get like the comparing both dates, what have improved and not. And by myself, I deal like more than 2 years with quantum computers, mostly remotely, of course. I don't have one at home. So my experience is on IBM's quantum computer. I have access to that, and you all can have access to that too. So just go to or type in IBM Quantum Composer in Google, and then you can make an account and try it out. And additionally, I'm on Stack Overflow, and there's a section called Quantum Computing, Stack Exchange. And I read a lot of questions. Of course, I read more than I can answer because it's quite difficult with the equations. They are getting really complex. So I also answered basic questions. Then we are Mimacom, or we are IT corporate, and in future, I think it will expand the business, also cloud engineering, that we can use quantum computers to make to increase our business sectors. So, and this is what I told you. I programmed already on quantum computer, and today's targets are getting basic understanding of quantum computing and also experimental practice. So with experimental practice, it's not that we're going through to IBM and say, hey, we want to program now on it, more that we can imagine what does it mean in practice. So what is a quantum computer? We normally know that normal computers have 1 or 2 CPUs and GPUs. And there are also some supercomputers that have thousands of CPUs and GPUs. and they're quite really good, to be honest. I think a supercomputer can do a lot, but to be honest, a supercomputer is not as super as you expect. So that's why we need a quantum computer. This is IBM's quantum computer, and they're working on the law of quantum mechanics. So we will see later what is quantum mechanics. And instead of normal classical bits, they're working on qubits. And of course, they can solve more complex problems than the other ones. So, as I said, supercomputers aren't that super for super complex problems. So that's why they are outdated for really complex problems. Because normal problems, they're getting added together. Like you have complexity of 2, then 4, then probably you have +2, 6, and exponential problems like 2 by the power of 4 or by the power of 6 will get super complex. So you have a matrix, and this you can't solve on normal computers. So that's why we need them. And how do they work? This will be my second episode in total. We look only roughly on this, how it works. It has a normal container, and the container is called cryostat, and they need to be super cool. So it's a superconducting quantum computer, and around like close to 1 Kelvin. So it's this is something really interesting. They are more cool than outer space. So we have something on Earth. There's so cold that you can't achieve by nature out of space. That's a really good achievement, I would say. Then next is they need to have a low temperature, as I told, and to get super cool and work. After this, you need to package all the qubits in little containers that they can stay cool. Because you can imagine if you have a big cryostat with a lot of qubits and you just cool the whole thing, that there will be some parts that aren't cool. And that's why you need to have little containers where you put in a qubit and cool them extra. So they all have super cool condition. And you get the data from the data center. Let's say you have a big area, and outside there's a data center, and you need to transfer the data into the cryostat for the qubits to calculate. You can achieve this with really big cables and let the information through the cryostat. And of course, they will receive it with cables inside, and to start to process the program or what you programmed or something like this, or calculate. And the whole thing will look like this. I have a magic tool here in PowerPoint. Is the laser. I never tried that before. Let's do it right now. Perfect, it works. So you can see here, there are the cables from the data center, and they're going in through. Here is like at entrance area for the cryostat, where the cable gets through to the cryostat. And of course, this is open for a viewing purpose, but normally this one is closed as a container. And you have super thick cables also inside to get the information through. This is the most of all optical processing, because that's what is working best in a super cool area. Then next, what is a bit? We all know a bit, like from our smartphone or computer. They're normally transistors in a silicon chip, like this one here. So if you have in a transistor a low voltage, it's a 0. If you have a high voltage, it's mostly 1. And this is basically what a bit represents. And a bit means is short for binary digit. So either 0 or 1. And this is how it looks inside the chip. So then we need to know that the bit is physical. There's no spooky magic inside. And it represents only 1 or 0. And I think we have all a smartphone or a laptop, and you need to understand there are billions of human-made transistors in a really small space, like 100 atoms. So this is human-made, And I think this is super, super impressive. Because in 1 billion, or let's say 2 billion transistors, there are only 100 transistors broken from beginning. So this is really insane. And I call this, to be honest, like the most amazing achievement of humankind. So to going to moon and back, I think it's fine. It's of course you need to do a lot, but you need to pack 1 billion transistors into, like, it's even smaller than I can show. And yeah, I think that's really impressive. And you can buy it for some francs in the shop. So you can just go out, or in your smartphone, you have it every day in your pocket or on your desk. So this is to be fair to the classical computers. They are insane already. Okay. And then the most interesting question, why you're all here, is not because of the pizza, I know. It's more about the quantum bits. Okay, we have here some, I think, connection problems. Oh, okay. What is a qubit, or quantum bit? What does quantum mean? A quantum is the smallest possible discrete unit of energy or of matter. So what is this? This is mostly like atoms, like a proton or an electron or neutron. And this is the basics. We know in this word quantum bit, what is the basis of the bit? Is like matter or a proton, electron. Then what is a bit? I told before, a bit means what? It's short for binary digit, has two states. So now we resolve what is both. What is it together, quantum bit or classical bit? Then here in the Swiss colors, we have two protons. They have a positive charge, and we have one electron, a negative charge. Now I want to show you how does a qubit work. Now it's getting not really complicated if you listen carefully. So, okay, it's not my fault if you don't get it at the end. Thank you. Um, so the question now is, if you have two protons and one electron, which side do they choose? Do they go to the right side, to the right proton, or to the left proton? What do you think? Perfect. Middle? Middle? Also good. Okay, you're right, it's both. Why should they choose? They have no reason to choose. So they go everywhere through. They're orbiting around one or the second proton, or this is what I can show you here. They can orbit around both at the same time or at a single time here on the right one. Exactly, both is correct. So, and this is called the superposition. Normally, we know that a bit has two states, but a quantum bit has a full spectrum of states. So it can either be 1 or 0 or between. As you can see, if the electron is here, it is orbiting around let's say this is a 1 and this is a 0. Then it's between both. So you have a spectrum. You don't have only one. You have everything between. And this makes the qubit unique. And also, it's called superposition, that you have orbiting around both protons. Okay? And then let's take a look at the basics of quantum mechanics. What does mechanics mean? Mechanics is something you just use it, but you don't know what it is. But normally, if you want to build a skyscraper, you need to know how it functions or what is the mechanism of a skyscraper. Then normally you build a little model to see how it should look at the end. And the same is for quantum physics. If you build a model to explain something you want to achieve, you use mechanics. So this is quantum mechanics, a model of achieving something in quantum physics. And as I said, again, we have now achieved the superposition. It's a full spectrum in a qubit. So it's not 0 or 1, it's everything between two. So you have a lot of information in one qubit, you can imagine. So then, now it's getting more complex. We have a spin. A spin is I can show you. A spin is something you have in every proton, every electron, and every atom matter. Like you have a magnetic field, And it's like a needle of a compass. That magnetic field is like a tip that is going around. And this is a spin in a proton or electron. So every little particle has a spin. As we can see here, if you have a spin going here or a spin going here, the one is going this way around and the one is going this way around, like the animation shows. Now it's going the other side. And this is the magnetic field that's producing by the spin. And as I said, it's like a needle in a compass. So you can imagine, from the physics lessons that this is like a dipole. So it has plus and minus, and that's giving a magnetic field. And if you have ever the unfortune to need an MRI, you will see the concentration of the spins in your head. So if you have really high concentration from the proton spins, then you will see the white area here. And if you have less matter that can show the spins, then you will get a dark area or darker area. And now we want to know how we can achieve information to a qubit. We can say if the one electron is orbiting around the left side or left proton, then you can see it's a 0, the state of 0. If it's going through the right side, it's a 1. And now the magic is happening. If it's going around both, then this is both 0 and 1 at the same time. And the same exists, of course, for the spins, because they have all spins and the spins orbiting around, because a spin, as the name implies, is a movement. So that's why they're orbiting. So the same you can apply for the spins. If the spin is going down, this is just for showing purpose, of course. Going down, you have a 0. Going up, you have a 1. Going to the right or both, you have both. Then what is entanglement? The next question mark. Entanglement is like you have a perfect symmetry in a system. You have, as we saw, we have two protons. They all have spins. The electron has their own spin. So if one spin is going up and one spin is going down, or opposite, if one is going up and the other is going down, what they choose? What do they choose? Going up or down? What do you think? Okay. I think no, it's not. It's none. They don't choose something because it's legitimate to say now it's getting a bit complex, I know, but it's legitimate to say that they choose none of them. They're not pointing anywhere because they're in a superposition. They have all the quantum states. So they're not only pointing up or down, they're pointing in every direction at the same time. And this entanglement is the symmetry, or it's anti-parallel. And this is why you call it entanglement, because they're doing exactly the opposite or influence each other. If it's going down, the other is going up. Or if the other is going up, it's going down. And this perfect symmetry is not just in theory, this is also in practice. So this is really what is existing in quantum physics. And the correlation between these two qubits, that the one will affect the other, if you change the 1 to the 0, then the other will change the state too. Even you put them apart of each other. If you have the one qubit 1 kilometers away from the other qubit, they still have the symmetry at the same time. And this is something that was explored by Mr. Bell in the 80s. And this is called the Bell state between two qubits. And yeah. Right. You have some, we come later to this. So the question was, if you have several qubits that you, if they will affect each other, some pointing up and down, and I will answer the question just in 1 second. So this was the answer I gave on Stack Overflow. There was a question, how does this entanglement works? And you can imagine you have a start point with qubit A and B. Let's say A is Alice and B, or the second qubit, is Bob. So you have Alice and Bob. And in the base of the qubits, you have like a state like 0 or 1. And at this, before you measure the state, what is coming out of the calculation, there will be exactly equal at the same time. So you have random states 0, 1. You don't know what is the outcome yet before you measure. So it's totally different and random. But if you measure, you see here in the quantum teleportation, this is something going into the third presentation. You see, let's say Alice has the quantum state 0, Bob has the quantum state 0, and then at the same time they have 1, 1, 1, 1, 0, 0, 1, 1. So you don't know, but if you measure, you will know, okay, they have now exactly the 0 or the 1. And this correlation is called the Bell state. Okay, they affect each other. So this is entanglement. So at the end, I will come to the conclusion and tell you, of course, what we learned, because now it's a bit confusing, I know, but I try as best as I can explain. And now to the question, entangled quantum state. We know that in a superposition, they have all different states. So there can be 0, 1, or both at the same time. And the quantum state that is entangled has all this in the same time. Okay, so this is the question: which do they choose? I asked before, and they choose none of them because they're pointing everywhere at the same time. They're in all the states, and this is in a superposition, and called the it has a perfect symmetry, as I said, and is anti-parallel. So, and now you think, okay, this is super weird, spooky. Do we have this? And yes, we have it, because every chemical bond, like the water molecule, has own spins, and only the bond that they connect to each other, the atoms, is possible through spins, because they point in let's say 1 point up, or this is pointing up, this is pointing down. So they will have a correlation and attached to each other. So this is 70% of what we are made for. We are 70% water. So we are all quantum physical objects. And to your question, you ask if it's for all, if one is changing. So it's proved to 2 qubits, but if you have more qubits, there are some qubits that have the entangled state. So it's not applying to all. But if one is changing, the whole system is changing. That's why you can transfer so many information at the same time. Okay? Or do you have other additional question or more deeper details? Okay. Okay. But you will. Yeah, you will understand it. And if not, we can talk afterwards. Okay. Now a bit easier topics. We have Gamechanger in the daily life, of course, in communication. Through the qubits, you can give information 0 or 1. Then you can imagine if you can calculate with the qubits in the quantum computer, you can also solve exponential problems like how you can develop drugs. And this you can't with classical computers because the equations are too complex. And also encryption. This is really important for banks and finance, how you can encrypt data. And that's also what you can achieve with that, with the quantum computer. And now we make it super simple. I will go back to basics and with a real exam. So let's say you go to vacations. Okay, it's before Eastern. You all booked a flight, I hope, and go to holidays. So I go. And let's say you will pack a knife, a phone, and a headset. And of course, if you go into a plane, you can't put a knife into the bag and the phone and the headset because it's not allowed on board to have a knife. So you have 2 suitcases or 2 bags. Now we know what would I do? Of course, I would put the knife into one bag and the headset and the phone in the other bag. So that's what you call, or this is the condition. You want to have the phone and the headset at the same time. The phone and the knife, of course, not, and the headset and the knife also not. So the condition is we want to listen music on board. So we need a phone and a headset. And we don't want to have a weapon on board because we want to feel safe. And we solved it by our brain right now because we know that you can separate them. This is what I mean. We have a quantum computer here. We are quantum physical objects and we can solve it. But how does a computer solve it, or a quantum computer? That's the question we will solve now. So given, let's say, bag, we have two bags, we give 0 to the bag 1 and to the second bag 1, okay? So we put the knife into bag 0, the phone and the headset into bag 1. Then we can say, okay, this is we make it in a table. So this is in bag 0 is the knife with K, 1 is the phone here, and the headset is also in one bag. So on a classical computer, you will have the 8 possibilities to put everything how you want. Let's say you put the knife and the phone in bag 0 and so on. So you can see all the possibilities are mentioned here. Then our state is like this, okay? Like here. So knife in 0 and the same. The funny thing is it's different from the half. It's totally opposite. So why you don't put the knife also in bag 1 and the rest in bag 0? So it's also working. So this is for optimization. You can just half this table and then you know already the outcome. So, and now you can say, okay, we have 8 possibilities to put the 3 items in. And we have 2 conditions. We have a bag 0 and bag 1. So we can see here, this red line is the 2 conditions, bag 0 and 1 is representing this number 2. But you also have 3 items, so you just choose 3 items. That's why you have 3 number 2s. And to make it easy, you can say, okay, 2 by the power of 3 is exactly 8. So it's just, you can write it in another way. Okay, 3 items, 2 conditions is 2 by the power 8, because you have 8 possibilities. This is really important that you understand that. Okay. So, but the problem is, we know it. How does the does the classical computer know it? So we need to apply a score. We need to say or tell the computer what is the best solution, and that's how we do a score. How we do a score is we have a given configuration, and we have a good pair. We know the phone and the headset is always good in one bag, and we know the rest is bad. So we have a good pair and a bad pair. Let's make example. We make for the first row, we configuration. So the knife, phone, and the headset is all in bag 0. So then we know, okay, the good pair is the phone and the headset is in bag 0. This is fitting, okay, right? So you have a 1. Let's say this is a 1, a good pair. We have one number of a good pair. Then you say, okay, what is bad? Bad is that you have a knife and a phone in the same bag. So this is also 1, but there's also another bad pair. You have also the knife and the headset in the bag 0. So you know from what we have here, the equation, this is of course this is 1 minus 2. 1 minus 2 is minus 1. Perfect. And the same we can do for a second configuration. Let's say our good example, we know by brain. Okay. So we have a knife that is going into bag 0 and phone and headset into bag 1. So then we know this is a good configuration because they're in the same bag. But we also know we have no bad configurations because the knife is in a separated bag. Okay. So there is 1 minus 0. 1 minus 0 is 1. So the second score will be 1. And we can do this for all the configurations here. Okay. So I made it for you. So you see there are bad scores like -1, -1, -1, and 1, 1, and you can clearly see, okay, there are only two configurations that are good. As I said, here's the knife in back 1, and the rest is 0, and here it's opposite, okay? So that's what I meant with you can split the table in half to get the outcome, because just vice versa. Okay, so we know that we have a good configuration. Classic computer will go sequentially through this table, database, and search the good configuration. And the quantum computer can just have it, instead of going through, it can just point it out at once because it has all the states in the superposition. So it don't need to see if it's 1 or 0. It has all the qubit containing 1 and 0 in the same time. So you have it at one shot, and you will see the one shot later. And now we say we have 3 items. Okay, quite easy. 2, 2, 2 is the 2 by power of 3, 8 configurations. You have 4 items. You do the same as you can see here. You have by the power of 4 for the items. But what is if you have a lot items, like n items? Then you have 2 by the power n. Or you have 100 items. You see it's getting really complex. 2 by the power of 100 is a 1 with 30 zeros. So it's a large number. And to solve that, you need a quantum computer. Okay? So what if the problem is getting more complex? You need to take a bigger quantum computer. You need more qubits, okay? It's super complex. So going back to the example, we have now the score. How would we do this for the quantum computer? We can say we have 3 items, okay? And we know this one item can be in back 1 or 0. So in 2 conditions, if it's in back 0 or 1. The same is for the phone, can be also in both or here. So we know a qubit has 2 states at the same time. So we have it already. We can just say we put the knife assigned to 1 qubit called qubit knife, and the same for the phone, qubit phone, and the same for the qubit headset. So you just need to assign 3 qubits to that, because you know 8 possibilities is by the power of 2 by the power of 3. And if you have 1 qubit, you have 1 or 0 as we told, so you have the percentage 50-50. If you have 2 qubits, you have the possibility the outcome is 0, 0, 0, 1, 1, 0, 1, 1. So you have 25% possibility. And the same is, of course, for this. If you would go further, you have 3 qubits, you would get 8 possibilities, okay? So this is 12.5% possibility. So what we need, I gave us a hint, we need 3 qubits. This is called the calculation power. And we need the score, method, or algorithm. And we need a condition, what we want to achieve. This is how you would solve it. This is like how you would plan your project, to know what you need. Because you can't just go to the quantum computer and say, now I want to start, okay? And now let's say I told you that we have a large number, okay? So you can represent this number. This is actually the particles of the whole universe we have in the world. Every single particle in the world, or that's how many particles are in the world. Let's say it like this, okay? And to describe this number, you can just put it by 2 to the power of 300. And this is quite easier. You see, this large number is for qubits. You just need 300 qubits to get the same number. So then you can see the power of exponential, okay? So to solve this, you would need 300 qubits. And interesting is that the quantum computer from IBM has at the moment, the name of the quantum computer is called Eagle, and it's a private one. You can't access it. It's in research, and it has 127 qubits at the moment. So this is the highest number of real qubits in the world. And you can see with 300 qubits, you can describe every particle in the universe. So we're getting close. It's not that far away. And this is called the power of exponentials, okay? And let's move on. we're going to build today our own algorithm on a quantum computer. And this is called the Grover's algorithm. So this is really a complex equation. So I think it's too much to tell you too detailed. Okay. So I make a quick, simple example for you. So you have, or first of all, I think my throat is today more dry than the topic. So we made something much better. Okay. So let's say we have 4 cards. We have 3 different cards, I don't know, and 1 queen. And our target now is we want to hide, or no, we don't want to hide first. We want to assign numbers, okay? We want to say we have 0, 0 is card 1, 0, 1 is card 2, and so on. And queen is 1, 1, the 4th condition, okay? And now we want to say we want to find the queen. First of all, of course, we need to hide the queen. Then we're going to hide every card. So we don't know where's the queen. Of course, we will put it in a box, shake it, and then we don't know where it is. Okay, but I can't animate it here. That's why I made it like this. And and of course we have 0, 0, 0, 1. So we know we have condition 4. But what is 4? The number 4 is 2 by 2 is 4. So we know 2 by the power of 2 is 4. So we need 2 qubits. Okay. That's how you get the approach to it. And just really roughly, the Grover's algorithm, you have 2 qubits, and you want to get all the 2 qubits in a superposition, like having all the states that can represent it. You do it with a quantum gate. A quantum gate, this is a Hadamard gate. This is something you can make them in a superposition, okay? Just roughly for now. So you initialize the 2 qubits. Then you have an oracle. You see, oh, what is this? I saw it last time in maths, and then I quit. And you can see here you have an oracle. An oracle in quantum physics is a black box, so you don't really know what is inside. Okay, and it will convert the phase, as you can see here. It's plus plus plus, and here it's plus equal to plus plus 0. And we know before our queen is the 1, 1. So we want on a quantum computer, we want to make a phase conversion to the queen that we know, okay, we mark the queen now. This is the queen we want to find later. Okay, we just hide the queen first. This is what you do. And in a matrix, it would look like this. Okay, you see here is the queen, -1. And the Grover algorithm will take a diffuser then to say, okay, you remember we have the queen hide it now, and now we want hide every card. So when you do it with this gates, with the initial gate like Hadamard's, then you have C gates. They convert this from X, Y, and Z, the Z angle, or it will convert the phase. And here also you have a controlled C gate. So this is something I don't explain now. It's too much. Okay. So, but what you really do is you just flip the face of the others that you can't really see who's the queen. Okay. Yeah, it's an easy example. Sorry. Okay, I just make it together. Okay, you just first you make a minus to hide the queen, to mark the queen. Okay, this is my queen, and then you apply a phase conversion to have all the other plus and minus 2 to that all here are minus. So now you can't really see if this is the queen, or this is the queen, or this is the queen. This is just a way to show how the algorithm works, because we can't just explore unexplored. We just need to say, okay, we have now the queen and we want to find the queen. This is like you trick yourself. You hide the Easter egg and you want to find it by yourself. But this is how you prove. This is how you prove really that this is working. Because if you wouldn't know where's the Easter egg, then how can you prove it? You will search for hours or days, or I never found it. Yeah. So and then of course you're going to measure at the end. This is what we're gonna do. We measure, we hide the queen at 1, and at the end I can really say something. We will find the state 1, 1. in a quantum computer, that we found it back, okay? So remember, if we see 1, 1, we found the queen back. Okay, we lost her, nobody knows, but then we found her, everything is fine. Okay, so this is like the operators, the quantum gates. This is something getting really complex, some quantum gates. This is what we need. This is our operators. And let's move on to a quantum computer. Why not? So let's go to IBM. I still share the screen. I just want to find my site and I can really recommend this music. I like it from Circle. Uh, okay, I need to look here. Okay, first of all, we have 2 qubits here, okay? And you can see the state of the qubits are 0, 0. You can see. First of all, we said, okay, this is super easy, drag and drop, like a document. So I said it's a simple example, okay? So it actually is. So you want to initiate? Oh, okay, sorry. Thank you. Okay, now we have the state. You can see we have all the states 0, 0, 0, 1, 1, 0, 1, 1. Okay, and here would be written in code. So next we want to do is to say, okay, we apply the Z gates to make the phase inversion. Okay. So now we can see these 2 are marks, but that's not enough. I'm sorry, the screen is out. Thank you. Okay, thank you. So we can see this is not enough. What we do now is we need to initialize them again. And now you can see we mark now the queen. Okay. So this is the queen. If I explained right. Sorry. Oops. Sorry. Let's remove this real quick. Sorry, I made a mistake. It's just for explaining purpose. Sorry, where's the dot? Yeah, here, perfect. So we need to control this gate, first of all. You see, we controlled with the 1 qubit, we controlled the other gate. So the phase will be inverted. So first of all, if you place 2 C gates, we saw it was this line. So this is not enough. We need to control with the C gate is something complicated. I don't want to mention now. So this is something, yeah, just for explanation purpose. So we need to have control this to mark the queen. Now we know 1, 1 is the queen. Then next, we're going to initiate. And then now we're going to hide or diffuse. As we saw, we diffuse it now that we can't know what is what. You see now 3 are marked. And then we apply another C gate. So it will flip around the other X. Scroll down. So I'm not nervous. And then we have H. Now we put in a superposition again. Okay. So now you see the outcome is 1, 1, as we said. So we hide it first and then we found it back. Okay. So this is super lame, I know, because we just hiding and exploring. Yay. So as you can see, now this is how you measure. You would measure, and the code is here. So feel free to copy. I like copycats. And yeah, we have 1, 1. So now we probably have luck. We make a setup. Okay, we set it up on a real quantum computer, but you know what? In a queue of a quantum computer, you can wait even for days to get in the line to process the calculation. I made this for 1 week to get the examples done for the presentation. I'm glad I did it, because otherwise I would stand here and think, oh man, I didn't calculate the queue. So, but we probably have luck. Let's make 100 calculations. So we hide the queen 1,000 times and find it 1,000 times. Okay. And let's take the Quito, or what quantum computer can we take? I saw another one, Bogota, Colombia. Perfect. Holidays. Let's say we hide it here. We say this is our find queen, okay? Job. We apply job to the real quantum computer now. And now you see it's a job has sent. And let's see if it's finished. Yeah. So it's pending job, okay? Probably we have luck, we have not, I don't know, but we go back to the presentation while that. Here. Oh, we're still there, perfect. So, okay. So now you want to know what came out of this, okay? Results. This is the method we applied, remember? And we measured, or I measured for you this calculation once for 100 shots, and it was able to found the solution for 100 shots in 6 seconds, and it has like 4.9% found this state, and most of all it found the queen. Okay, so this is really interesting. I come to it later. So then I made the same for 1,000 shots. Okay, in 6.7 seconds calculation, and you see it's more obvious that it found it again. And now interesting, this is the maximum I can do on a quantum computer from remote is 20,000 shots. So I hid the queen 20,000 times and found it. And you see here it's really precise that you have more possibility to find the queen. You see here the 0, 1 isn't that high percentage anymore. And you can see in total, this is the timeline. And important is time is running in the system. So this run 11.3 seconds in the system. And now there's something really crazy. I hid it 20,000 times in just 11.3 seconds. So it was extremely fast, okay? Then it was super precise because you can see its evolution. If you get more shots, you get precise results. And you explored something unexplored. Because you see here, I made a 0. Before, if we would do it 100 times, which would just think, okay, hey, this is just these three possibilities. But in fact, if we do it more often, we see, there's another state, the 0, 0. So we were able to explore a state that wasn't explored before because we did it more often. Okay. So then I did the same with my result. I draw a card. You see, I'm not a good drawer, so that's why I'm in IT. Okay. So 3 times, and I made a queen. So super beautiful. And I was doing it by myself. I did it like, let's say 20 times. Okay. And I measured if I could find the queen or not. Okay. And I found it, let's say, on every second or third shot. So on the bad half. Okay. Second or third shot. And in 3.2 seconds, I found the queen in average. And you can see I took, if I would do it 100 times, I would take 5.33 minutes to find the queen. The quantum computer did it in 6 seconds. The same is, of course, I didn't do 1,000, I calculated up, okay? So I have also work to do. So this is my workday, loggings. So in 6.7 seconds, and you see 53 minutes I would take. And for 20,000 shots in 11.3 seconds, I did it, or I would have done it in 17.7 hours. Okay. So you see the quantum computer, okay, it's 50 times faster. That's okay. Okay. Then you see, oh, whoa, it's 500 times faster. And then even here, it's over 5,000 times faster. And I was extremely slow. And I was super imprecise. And I explored nothing. Okay. So this is the comparison. The classical computer. This would be something between. It depends. I think it would be something between me and the quantum computer from the time. If you have the speed of the classical computer, because you just build it up, you let the program run and run and run. And the problem is on a classical computer, if you would run this experiment, it need to set up so it's not in total that fast, because the quantum computing is making hiding, finding, and the normal classical computer need to rerun the program. Then it has a lag in the program. You know, sometimes it's taking. I would say it takes more time than than me, but less than a quantum computer to make the whole calculation, because you just rerun and it's going sequentially through the task. But a quantum computer just reveals it by one time. So I go through this card, this card, this card. But as you saw, the quantum computer is just revealing everything at the same time. It's like I would lift up the 4 cards at the same time to find the queen. So because it has all the states, as you remember in the superposition, it has either a 0, 0, 0, 1, 1, 1, and so on, or 1, 0. So you need to go through by hand. And in a superposition, you can reveal everything because you have everything in package. Okay, it's like you can say, I want cola, I want Red Bull, and then you just grab one, but a quantum computer has everything. They can provide you both. Okay, so that's why it's faster. Because in a bit you have 0 or 1, and in a quantum computer you have both at the same time. Question solved? Not convinced? Okay. Okay. What we learn, it's not spooky. We're all quantum physical objects. And it has more density of information because you have every state you can access at the same time. So you have less bits to provide more information. Then the problem is not that this is not possible by calculation. It's because you don't have the tools to calculate it. Okay, the algorithms need to be found. Then, of course, no quantum computer is faster than a classical computer because some problems need to be solved by classical computer. For instance, if you would say you have 9 guests and you say each guest hates each other, and you have a table and you want to seat every guest on the table, then you don't know where to put them because you can't solve where to seat them because they they don't like each other. Okay. So this is something a classical computer would never solve because the problems are too complex if they get exponential, okay? So linear problems are good for classical computers and exponential problems are good for quantum computers because they don't have the computation power. And as we saw, we explored something on a quantum computer, so we can also explore something about us. And we learned today about entanglement. So this is like the spins, the symmetry and antiparallel, that they have a correlation. This is called the entanglement. Then the basis of quantum computing. And we compared both classical versus quantum computers. And how does it work? Just roughly, this will be my second presentation. This is then also more easier presentation because we just build up a computer. If we have a lot of money, then we can build one, of course. And we learned about qubits. What is a bit? What is a qubit? And superposition, that they can have orbit around both at the same time or on the single ones. And we saw the daily examples like communication and encryption, what is possible with that. And I want to give you, even you don't understand everything, as I told before, I make the question mark smaller, not away or disappear. So I hope you still like me after this. The link to remember even the qubits, okay? I just want to give you the qubits information. What is it? I have a daily example. You ask a friend to go out on the weekend. Okay, so we all know that the friend is often say maybe. Perfect, maybe. Everybody knows it. I like maybe because you don't know to plan or not. But it's fine because this is a quantum statement, I would say. Okay, because maybe can be yes or no, like 1 or 0. Okay, this is before you measure the qubits. Okay, before you say, okay, now I want to know the outcome. This is the state. You have a maybe. You have 1 or 0. Is he coming or not? And the same is, and now the weekend is coming closer to you. Okay, you want to go to the cinema, you want to buy the tickets, but you have time pressure now. Yeah, now you ask again, hey, are you coming or not? And then this is the measurement because you make it fixed. You want to know the outcome of the friend. And he says yes. I just could also write no, but yes is more happy. So I wrote yes. Okay, he's coming. And you have the outcome. Now it's a 1. And this is exactly what is after measuring the experiment. We know that there is the queen or not. We know he said yes or not. So that's the difference, is that qubits can have both, or it's like maybe. So if you ever say maybe, you gave a quantum state to your friends, okay? And if you say yes or no, it's also fine because you're old school, you're a classical computer, okay? So, but I like it, okay? So this is what I told you. It's 1 or 0 at the same time. Probably I should shown this before, then you know. And what's next? Okay, the next time is the quantum computing, how to build a quantum computer. Lunch and Learn in 14th July 2020, episode 2. And in before Christmas, we have a quantum computer in detail with teleportation, episode 3. And I want to thank you very much for listening.